we are still talking about polynomial functions, right? So for once and for all, polynomial functions are functions that have your variable x, and that variable is raised to an exponent, which is 0 or a positive integer. All right, so x to the 0, x to the 1, x to the 7, and so on. Square root of x doesn't work. 1 over x doesn't work because that's x to the minus 1, right? So that's what a polynomial is. The degree of a polynomial is the highest exponent to which the variable is raised, right? So if we normally write the polynomial this way, and so you see here, you have a sub n, x to the n, that's an exponent. And then if you look at all of the other exponents, it's n minus 1, smaller than n minus 2, smaller, and then, dot, 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 all the way to 2, 1, 0 for the exponents. So this implies that n is the highest exponent. That's the degree. And the coefficient of the term with the highest degree is the leading coefficient. Okay? All right. So here are some examples of polynomial functions. This is a constant function where the degree is 0. Degree is 0 means, for example, you have f of x is equal to 3. Now, where is the variable here? Well, it used to be 3 times x to the power of 0. Okay? But x to the 0 is 1, so that's just 3. So this is degree 0. This one, for example, what is the equation for this one? Y-intercept is 3, and then, so y equals x plus 3, right? So you see here there is an exponent of 1. That's the highest exponent, so the degree is 1. Here we have a parabola, and you know that that's a quadratic function, right? So the degree is 2. Yeah.
For the top equation with the highest exponent, is n a number?
N is a number. It's an integer.
So what if it's just 1 and 2 is higher? You know what I'm saying? Is n always the highest?
Yes. That's why it's listed as n, and then n minus 1 lower, n minus 2 even lower, n minus 3 even lower, all the way to 2. Well, that implies that they're dropping down to 2. That's, yeah. Okay, so graphs of polynomial functions share some characteristics. So take a look at this polynomial. This is a polynomial function, right? So look at what it says here. Polynomial functions are, number 1, defined and continuous for all real numbers. All right? That means there are no values of x which you cannot plug into the equation, right? So it's defined. The domain is negative to positive infinity. There are no values of x which would make f of x undefined. And it's also continuous. Continuous means you can draw a polynomial function from beginning to end without removing your pencil from the page. All right? Furthermore, this is a meaty sentence here. They have smooth, rounded turns. That means no corners, no cusps, okay? So no corners. Okay? All right, so here are examples that are of functions that are not polynomial functions. This one here fails because there is a discontinuity. Any type of discontinuity means it's not a polynomial function. This one fails because it's a corner. Okay? All right. Yeah.
Sorry. So let's say
remember we talked about even and odd degree functions. Something that resembles x squared, right? A parabola, which is symmetric around the y-axis, is even. Something like x cubed which is symmetric around the origin, is odd degree, right? So let's graph these. So for the first one, 4x to the power of 6, what do you think, even or odd? Even, right? And remember we talked about how to graph these before. So at 0, x is 0. Now, this has x to the 6. That means for each unit that you move along the x-axis, you go up to the power of 6 of that. So if I go over 1 unit, I have to go up 1 to the 6th, which is 1. Times the 4 in front, I go up 4. Okay? Now, at x equals 2, right, when I move over 2 units, I'm going to go up 2 to the 6 times 4. So that's super, super high. That means I know that this is very, very narrow. It doesn't even hit y equals, it doesn't hit x equals 2 in that middle, right? So it goes up like this. Okay? Not NASA precise, but good enough, because my first point and the 0 are completely precise. And then I know that it's never going to hit these points at x equals 2 because it's got to go up higher. Okay? Yeah.
When you multiplied it by 4, why did it get so smaller?
What got smaller?
Like, isn't it like if you move 1 and 1?
This next one is a cubic function. And we know that's like the, that's like the vertical snake shaped, right? Except it's going to move right 4 and up 1. So the center will be here. Now, this moves up like the cube of x, all right? That means if I go over horizontally 1 space, I'm going to go up 1 cubed, right? 1. And it's got to be, it's an odd function, so it's symmetric around the its origin like that. And now if I go over 2 units, how much do I go up?
8.
8. So that'll get me up to this 9 right there. Okay? And here. Yes, question?
Yeah, so an odd function, basically what happens on the left side of the y-axis is reflected on the right side of the y-axis?
It's symmetric around the origin.
Okay.
Okay.
But this equation isn't symmetric on the origin because it's been moved.
Right.
So would it
But
still
it
be
started, the
an odd
parent function is an odd function. So remember what we said, they resemble the graphs of x cubed, okay? All right, let's go, okay, leading term test. This is extremely important. You need to be very quick on your feet by the time we end the chapter with this leading term test, all right? So what we're gonna do is we're gonna use the leading term, that's the term with the highest degree, in order to test for end behavior, all right? So what we do is this. Again, if you have a polynomial function and n is odd, right? So it's x to the power of 3, 5, 7. N is odd. We know that one end will go up, one end will go down. Now, which end goes up and which end goes down, that depends on whether the coefficient is positive or negative. So, for example, if I have f of x is equal to 3x to the 5, this tells me one end is up, one end is down. The fact that this is positive tells me it's up on the right and down on the left. How do I know that? It's positive 3x to the 5. So if my x's were positive, 1, 2, 3, and I plugged positive values in here, this whole thing is going to remain positive, so it's going to be above the x-axis. If my x values were negative, negative 1, 2, 3, that will make this a negative value, so it'll go down here. As opposed to, if I had, for example, negative 3x to the 5, now for positive value, oh, I put it in the wrong spot, sorry, here. negative 3x to the 5. Now, when my x values are positive and I plug them in here, the y value is negative, so it goes down, and vice versa. All right? Now, when n is even, they either both go up or they both go down, right? So how do we know whether it's up or down? Again, leading term test. So if I have 2x to the 6, both go up. If I have negative 2x to the 6, both go down. Okay? So this is how we use the leading term test. All right, let's do this one. So here's a random function, and we're going to decide, without a calculator, without graphing, without knowing how the graph looks, what the end behavior is, right? So it says to describe the end behavior. This is now code. Nobody's going to ask me what that means. When you see describe the end behavior, I want to see this. Limit f of x as x approaches infinity. Limit f of x as x approaches negative infinity. That's what end behavior is, right? It's going to be like very clear. Now, here's what I do. I pick the leading term. The leading term is the one with the highest coefficient, with the highest exponent, not the first one, the highest exponent. So here. And I take that entire term along with its sign, right? So now I have 3x to the 4. So think about it. For positive x's, is that value going to be positive or negative? Positive. So it goes up to positive infinity. For negative x's, what is that going to be? Positive. Okay? It's as simple as that. Let's do another one.
Why is it going positive?
Because if you put like negative 1 in here, to the power of 4, that's positive. Okay? Let's do this one. What's the leading term here? Negative 2x to the 5th, right? So it's not the first one. This one is not written in standard form, so it's the second one. Be careful. Okay?
I got messed up.
Yep. It's the same thing here,
like
but it may not have
usually
been.
over,
Yeah. Okay, so here. Limit f of x as x approaches infinity. Limit of f of x as x approaches negative infinity. So for positive infinity, here, what is it going to look like? Negative or positive? Yes. Negative. And what about for negative infinity? Positive. Right? And we spent way too much time on this. When you're doing it on your own, there is no discussion. It's got to be boom, 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 quick. These are your freebie points. All right? Okay. Now, x-intercepts. Again, these are all things that you've seen. Now we tell you again for the last time, and then we never teach you this stuff ever again, right? To find the x-intercepts, all right? So think about it. X-intercept are these points. What's the y value at those points? 0. Y is 0. Y is the function. So think in those terms. The function is 0. So what I do is set f of x equal to 0 and solve for x. Okay? The x-intercepts are also called zeros, roots, and solutions. 4 synonyms, all right? All mean the same thing. Okay, turning points, it's exactly what it is. What do you think those are? Those are points where the graph does what?
Turn.
Yay, okay. So, in more technical terms, these are the points where the function changes from increasing to decreasing and vice versa, right? We don't say the graph turns, it changes from increasing to decreasing. So here's the deal about turning points. If a polynomial function has degree n, right? If the degree is n, it has at most n minus 1 turning points, right? At most n minus 1. So for this one, 3x to the 6, right? 6 minus 1 is equal to 5. So this could have a maximum of 5 turning points. Does this graph have 5 turning points? It doesn't, but it's got less than 5, so that's good. Does that make sense?
Why would it be
Yeah. Yes and no, yeah.
Wait, how do you know it's going to be the maximum?
So, the degree then tells you 2 things. First, maximum turning points, and also maximum number of zeros. Whatever the degree is, that's the maximum number of zeros a graph is allowed to have. So here, for example, if the degree is 6, it's allowed to cross the x-axis 6 times. Now this one crosses how many times?
3 times, yeah. 3 times.
Right, so it's allowed to cross as many as 6 times. So it can never have like 7 zeros. Now of those 6 zeros, some will be real and some will be imaginary. All right? Okay, let's take a look at this one. It just says state the number of possible real zeros and turning points. Those are the imaginary ones. Yeah. Okay, so how many zeros will this have? How many possible zeros?
3.
3. And, right. Okay, so the degree is 3. All right, that means 3 possible zeros. Okay. 2 maximum 2 turning points. Okay, now it says determine all of the real zeros. So how do we determine the zeros? It's going to be f of x equals 0. So we're going to take this function factor it. Okay. X plus 4, x plus 1. So what's x equal to? Right? So you see that it does indeed have 3 real zeros. Right? So this is how we're going to figure out all the zeros. And then with this, you'll also come up with imaginary and so on. All right. This one, I'm not going to, reteach how to factor this. So this, any type of factoring, you need to remember from Algebra 2. Yeah. This one, I've guided you and I've told you this is quadratic form. This is the last time that I will give you that benefit. How do you recognize that something is in quadratic form? Well, you've got a constant. You've got an exponent here. You've got a term with an exponent. And then the other term is the first exponent squared, right? So x to the 2 and then squared x to the 4. Or it'll be x cubed, x to the 6, x to the 4, x to the 8. So now when we factor these, first of all, what is the maximum number of zeros?
4.
And turning points?
3.
Okay, so let's factor this. We're going to set it equal to 0 first. Now when you factor, it's x squared and x squared. Right? And minus 3. Oh. These scenes are so pretty. It's almost depressing because you're not there. It has the opposite effect. Okay. So -3, -5, right? And then when I solve these, I'm going to get that x squared is equal to 3. So x is plus or minus root 3. X squared is equal to 5. X is plus or minus root 5. So you see that you do indeed get 4 distinct solutions. They're real solutions, but irrational. Okay? So 4 real, irrational solutions. I mean, it doesn't really make a difference whether it's rational or irrational. Like those, we got rational solutions, and these are irrational. But all real. Okay, here, same situation, right? You've got x squared and x to the power of 4. Again, 3 turning points, 4 zeros, blah, blah, blah. X squared minus 3. X squared minus 1 equal to 0. So x is plus or minus root 3, plus or minus 1. So you get 4 solutions, 2 rational, 2 irrational, all real. Okay, multiplicity, my favorite thing of all. If a function has repeating zeros, right? So for example, if you have f of x equal to x squared. How does this factor? X plus 5 squared, right? Yeah? So then what's x? Negative 5. Okay, so it should have 2 solutions. We got 1, but it's a repeating one because it's x equals negative 5 and negative 5, right? So that's a repeating 0. It could repeat twice, so it could be, to the power of 2 or 3 or 5 or 7 or 6 or 9. That's a repeating 0. If a function has a repeating 0, the multiplicity of the function is the number of times a 0 repeats. Now, this is, okay, so a 0 is where it hits the x-axis, correct? So this function hits the x-axis at negative 5, is that right? Okay, how does that look though at negative 5? How does this look? Here is negative 5. This parabola looks like this, is that right? Okay, so here is multiplicity. If a function has an x-intercept of even multiplicity, so to the power of 2, this has a multiplicity of 2. The graph touches the x-axis at the point of intercept and turns around. So just like this one, it touches it and then it turns back around. If a function has an x-intercept of odd multiplicity, right? Then the graph crosses the x-axis at the point of the intercept. So that means if it was, like x plus 5 to the power of 3, then it would have crossed the x-axis. All right? So if it was x plus 5 to the power of 3 at negative 5, it crosses the x-axis. All right, so even and odd multiplicity. And this is how, in conjunction with this is how you'll figure out turning points as well. Okay, this is what I just said, but I just said it better, I think. Okay, here we go. This is it, putting it all together. We're going to apply the leading term test because we need to figure out end behavior. We're going to determine the zeros and state the multiplicity. And then we're going to graph the function. Now the first one, I kind of helped you out. I factored it for you. So I've given it to you in factored form. You should always take a look and factor it. Now, the downside, if you have the equation in factored form, is for the leading term, you have to unfactor it. You have to multiply it out. But you're not going to multiply the whole thing. What are you going to do? Just the leading terms, right? So for the leading term, we're going to take the x times the 3x times the x squared, right? So that'll be how much? 3x to the power of 4. Okay? So just take the highest, the leading terms of each monomial. Okay? Of each binomial. Okay, so now, with this, the limit of f of x as x approaches negative infinity is what? Positive infinity. And the same for the other side. What does this tell me? As x approaches negative infinity, this is going up. As x approaches positive infinity, that's going up. So I put those little guiding arrows for myself. Okay, what are the zeros? Right, x is 0, negative 1 over 3, and 2. There are 2 2's, it's repeating. So here is what we're going to do. You guys are getting ahead of me. So we write it like this. Now, for the ones that have a multiplicity of 1, we just leave it. And then for the ones that have a multiplicity of 2, I just say multiplicity of 2 or higher. Yeah. So there is a 0 at 0, 2, and negative a third here. Now, the one where there is a multiplicity of 2, that's the one on the far right. The graph is going to come over and turn around, right? The other ones have a multiplicity of 1, so the graph is going to cross it. Now, on the far left side, the graph goes up. So that means if I'm going right to left, it's going to go, I'm sorry. It's going to go down like this. And now, it has to cross it because it's got a multiplicity of 1. But now it's got to hit that second 0 at 0. That means somewhere in the middle, it's got to turn back around and go up. Okay? And now, what is it going to do? It's got to turn back around to hit that second 0. But here we've got a multiplicity of 2. So it's got to turn around and go back up. Because there is a multiplicity of 2. So this should say y equals, so we can graph it. Okay, leading term, negative x to the 4. So limit of f of x as x approaches negative infinity is negative infinity. And as x approaches positive infinity, it's also negative infinity. So it goes down on both ends. Zeros. We're going to set this to 0. Factor out a negative x squared. So I get x squared minus 4x plus 4 equals 0. We're channeling our algebra knowledge here. Now I have negative x squared, and here it's x minus 2 squared is equal to 0. So my zeros are x is 0, multiplicity of 2, x is 2, multiplicity of 2. Okay? So x is 0, x is 2. End behavior is down on both sides, so it's going to look like that. Okay?
So you can leave those arrows disconnected.
Yeah, those were just guiding arrows, right? So I know which way to take the graph. Yes? Uh-huh. And then it would cross the x-axis there. Okay, now going backwards, find a polynomial function of degree n with only the following real zeros. More than one answer is possible, right? Okay, So find a polynomial function of degree n with only the following real zeros. So here's what I want you to do. N is equal to 4, right? Again, more than one answer is possible here. N is equal to 4. That means all of the exponents together, right? They have to have a maximum of 4. So here's what I mean. So f of x is equal to, if it's got zeros of 6 and negative 3, that means it's got a factor that looks like x minus 6 and a factor that looks like x plus 3. Is that right? Now, what would be the degree of this as it is now? 2. But I need it to be 4. So I could do square and square, or 1 and 3. Yeah, that adds to 4. Or x minus 6, what option did I not do? 3, right?
Could you not put the square in the middle?
Or,
Did you not do x squared outside of it?
Yeah, because then there would be another 0, which would be...
well then yeah,
Oh, God.
then you would have x equals 0 as well. Or you could do, like, I don't know, x minus 6 squared, x plus 3 squared, like we did over there, but be a rebel and add a coefficient, right? I know. I mean, right? Why would you? I mean, but you could, okay? So that's why it says more than one answer is possible, and obviously I'll look for,
If you do that on
right?
testing, you'll be wrong.
Okay,
Don't have it factored.
so this is due tomorrow. Huh?
What if we don't write it factored on there?
What do you mean?
Like we write things down, like the...
You could also, listen, if multiplying is your thing, you could multiply this out and give me the equation in standard form. Great.